So basically last time we started out with the idea of discussing proximal gradient descent, and this is basically the advanced version of the gradient descent which we already studied in our last lecture. So what we observed is that this particular proximal gradient descent is applicable to all the convex functions which we have discussed till now, but it extends its role to the functions which are convex, but if they are not differentiable, then also we can use these proximal gradient descent in that scenario. Whereas in case of gradient descent, we cannot do that because this particular cost function, this particular algorithm is only used for convex functions. So in line with that, we saw that this is the loss function that we last time were focusing on, and what we saw is that this particular cost function is indeed convex, as it has a single minima at this point. But other than that, you can see that it's not differentiable at this point, because you can see it has a non-differentiability at this point because of this corner this particular function has. So in this type of situation, if you try to run the gradient descent, it will not work, because if you start doing gradient descent on this particular loss function, what you will observe is that once you reach at this point your gradient is not calculated. So if the gradient is not calculated at this point, you will not be able to get to the local minima, and your basically your program will throw an error because gradient is not calculated here. So in order to avoid this type of situation, we try to form these proximal functions which we discussed last time. So what are these proximal functions? These proximal functions are nothing but they are convex functions which we will derive today. We will see what these convex functions are. So once we come up with these convex functions which we are calling as L prime, and note that this prime is not anywhere related to the derivative, it's just the convention I am using here. So it's a convex function, and the three important characteristics of this convex function are that at one point it has to coincide with the original loss function L theta. So that is why I am putting it over here. And the second one is it has to be on top of the loss function L theta. So on top of it means it has to be a upper bound on the loss function L theta. So this is important, and we will see how we will make use of it. So it's a upper bound on the loss function L theta. And the third one is that first is convex, second is touching of these points, touching at this point, and the third one is upper bound. So three constraints we have to keep in mind in order to make this particular proximal gradient descent work. So what we saw is as you progress down in the iterations, so these are all iteration numbers k plus 1 and k plus 2. So as you can see, as you proceed down with the iterations, the convex function keeps on changing. So it will be some other convex function at this point and some other convex function at this point. So at the extreme point where you have this discontinuity, at this point if you consider this black function, what will happen is, if you initialize your gradient descent at this particular black convex function, then you can go for gradient descent very easily, and then you will reach to the minimum of this black function. And then what you can do is, once you are at this point, you can project back onto the original loss function L theta, and you will get to the minimum value. And the important point is that for this particular function, which is the black function, your gradient descent is valid. The gradient you can easily calculate, but at the same location for this loss function L theta, where we have this pointed curvature, here L theta derivative of the loss with respect to theta is not valid. So what we do is we calculate minimum up to this point and project it back onto the original loss function L theta. So this will give you the minimum value for L theta. So this was the progression of your proximal gradient descent. As you can see with iterations how we are progressing down with iterations, and you can see how at the last point we hit to the minima and get to the minima of the complete loss function L theta. So this was the mathematical way of describing the above description which I had discussed. That is to our objective is to find L prime k, where k is the iteration number, so that is not valid here. But still, our objective is to find L prime k, such that the new loss prime, the new function which you will form with, has to be greater than the original loss function, and it should touch at the value of theta k that we have also discussed. So using these all above constraints, which I have told you, what we do is, if we are minimizing on this loss function L prime, what we are doing is we are going down in the loss theta function L theta. So that is the basic understanding of it. That is, if you minimize on this loss function L prime theta, what you are effectively doing is you are actually going downhill onto the original loss function L theta. So this is quite evident from this diagram also. As you are going down, as you are going down on this each of these convex functions, you are actually making a step towards the right to move towards the minima of the original loss function L theta. So once you are in this point, you again go down. So basically you are moving from here to here. So compare it. So basically these units like theta k plus 1, theta k plus 2 is somewhat, you are going down the hill onto the original loss function. So what we started out with is, like, we wanted, our aim is to get to this L prime k. So in order to do that, what we saw was, like, this is the original function that we have, this one, and what we did is we added and subtracted two values, specific values at theta k. We added these two specific values and subtracted, so it will not create any difference here because you are adding as well as subtracting the values. And then you expanded the a plus b notation here. So we have a plus b thing. So what you do is you write it as a square plus b square plus 2ab. So that is the same thing, which is this one, a square, this is b square, and this is 2ab. And this is the same one which we have already, which we already have along with this expression. So now what we saw is, like, we now we again repeat this expression which is on the top. So here, if you see this one, what we are trying to find out here is we want to find out the expression which depends upon theta. So what we saw is the only expression which depends upon theta is this one. As you can see here, we have this theta to which this L theta depends upon, and similarly we have a theta here also which depends upon, there is one term here also which depends upon the theta. Whereas this term which you see here, this one is actually completely independent of theta, and we are calling it as gamma k transpose. So this is gamma k transpose, so keep this in mind. So so this is basically independent of theta, whereas this is also independent of theta, so we call it as beta k. Now I have explained you all this last time also, but remember that once we are doing you can see we are upper bounding a matrix times the vector norm, L2 norm of that by the operator norm of the matrix times the vector. So once we are doing this upper boundation on this, once we are saying that this particular term is upper bounded by this term, that means you are actually finding out this expression, this L prime k. As I told you that L prime k is upper bounded on this loss function L theta. So what we are trying to find out is the L prime k. So once we apply this constraint of upper bound, which is this one, that means if you write the expression in the red one, that is actually nothing but it's L prime. It is nothing but L prime theta. Why it is that? Because you are finding the maximum value of this. So the maximum value of this is already this one, and if you use an expression that involves beta k and this term, then you are actually writing it in terms of L prime k. So this is basically L prime K, which is equal to this term plus this term plus this term. So what I am doing now is, instead of writing x operator norm square, I am substituting that value by 1 by eta. So if I substitute 1 by eta onto this particular, by replacing the operator norm by that, then the complete expression will become like this. Same expression only. So beta k is nothing but this beta k, then this is replaced by 1 by eta times this expression plus gamma k transpose times theta k minus theta, and then lambda times phi theta, psi theta. So this is basically the expression that you will get for L prime theta. So remember, now this one is the function L prime theta, which is the one which you wanted to find out. Remember, so we have found out this expression. Earlier expression was L theta. Now this is the new one which we are trying to optimize, because this is the convex function actually. So now what we will do is, we will try to find the minima of this loss function. See what we were doing here, we were trying to find the minima on this loss function L prime theta, right? So we will be trying to find out the minimum point on this and see what how we will do that. So here if you see, what we are trying to find out is the theta k plus 1 that corresponds to the minimum of the new loss function which you have recently found out, which is this one. This is the new loss function. So now this is the one which we have already now with us. We have already calculated and just replacing it. Now what we are doing, we are multiplying eta on all the sides. So if we multiply with eta on all the sides, it doesn't matter because it's just a constant. So constants do not affect the optimization problem. So they are just the constant. So we are just multiplying eta with all the sides here. So once it is done, then what we are doing is, we are actually writing this in a different fashion. So we are writing it in this way. So it's an A transpose A, which is nothing but A2. So I'm just writing it as A transpose A. I'm using the matrix identity to write it like this. And now if you see this one, this is basically I want to write a complete square for this particular expression here. So it is basically right now a square plus 2ab. So what I am doing is, now I am writing it as a plus b whole square minus b square. So basically this is basically a square and this is 2ab factor. So what I am doing is, I am writing it as a plus b whole square and then minus b square. So I'm trying to write in that way. So we are replacing the a square plus 2ab by a square, a plus b whole square minus b square. So this terms which are here will be replaced by these terms which is given over here. And this is the original one which is over here. So this is all mathematically algebraic manipulations which I am doing. So there is nothing rocket science over here. It's just simple manipulations of the terms. So once we have this, what we do now is we observe here two important things. That is, we call this particular expression, specifically this one, as zk, and we call this also zk because both of them are same. This one is also same and this is also same, so we're calling it as zk. And this is all the other terms are remaining the same. Now what we are doing, we are actually minimizing onto this loss function theta, right? So we want to see which of these terms are actually dependent upon the theta. So when we see which of the terms are actually dependent upon theta, we can observe that this is not dependent on theta, this is also not dependent on theta. The only terms which are dependent on theta are this one and this one. So if I am writing this particular term as zk minus theta, then we have this zk minus theta transpose zk minus theta, which is nothing but the L2 norm of zk minus theta. So this completes, actually represents this whole expression. And then we have this thing over here. So both of them are here. So So now what we are doing is we are actually minimizing onto the L prime function, which is the proximal function. So if we are trying to minimize on that, that means, you know, you are finding the theta corresponding to it. So that theta is the optimal theta which you will get for the original loss function L theta also. So this is the way of doing the minimization. So if you see what zk is nothing but it is basically this expression which is inside. We replace zk by this expression. So I'm just trying to show you that what zk it's trying to do. So zk is theta k plus eta times gamma k. This is what this expression tells you. And we know that what is gamma k. Gamma k we already saw. We replaced gamma k here. You can see here this is actually gamma k transpose. This particular term is gamma k transpose. So if you take transpose of this complete term, it is x, it will be reverse, right? It will be x transpose y minus x theta k. So because this is gamma k transpose, you have to take transpose of this term. So once you take transpose of that term is gamma k. So once you substitute that value here, you will get this answer. And once you take the minus term out, you will get this. So can anyone tell me what is this expression? Have you seen this expression before? Anyone? Have you seen this expression? Can anyone tell me, have you seen this expression before or not?
Sir, can you show the expression one again?
Okay. This one. So this expression, have you seen somewhere? This expression, have you seen? So this means you people are not studying. Anyway, so this is basically nothing but, if you remember, it's a gradient descent. So if you go to the original implementation of the gradient descent where we started out with the matrix versions of that, you can see that you have this original theta k and then you are doing step size x transpose x theta minus y. So this is the original expression for the gradient descent. So this is actually nothing but it's a gradient descent expression. And this is zk, it's a dummy variable here, but earlier it used to be theta k plus 1, if you remember that. So theta k plus 1 is theta k minus this. So this is the original, originally when we were discussing gradient descent, it was not here, it was theta k plus 1, but now it is zk. So what we observe is that this is the gradient descent. So the proximal gradient descent goes like this. So here what we have is, initially you assume that your vectors are all zeros, then your eta is, you know, in between 0 to 1 by x dot operator norm of that. So this is the initialization step. Then what you do is you do a gradient descent using this equation, and in this equation once you do the gradient descent you will get zk. So once you get this value of zk out, what you do is you actually apply that zk inside this cost function which is given over here, and once you solve for this cost function you will get theta k. And once you get this theta k, you check for the initial theta k with the new one theta k plus 1. If that is less than the epsilon naught, then you stop. Otherwise you keep repeating these two steps. These two steps will be kept on repeating, this one and this one. Once you satisfy these the difference between the consecutive thetas which are less than epsilon naught, then you will be able to find out the estimated value of theta, which is the actual theta for the parameters. So this algorithm, which consists of 4 steps, is nothing but it's a proximal gradient descent algorithm. So let me show you some examples for this, and then you will understand more better that what this is actually all about. So the 4 steps that are required in case of this algorithm is initialization step, then you follow the gradient descent, and once you have this gradient descent done, you use this dummy variable, the vector that you obtain here, into this particular cost function, and you get the value of theta k out, and then you check for the convergence criteria, that if this situation is not met, then you can go back to the go back and repeat the steps. So now let us see what we can do now. The important thing that I wanted to discuss along with this is, if you recall, I told you last time that this new function L prime k, which we are trying to find out and which we have already found out using this expression, is actually separable if phi of theta is the regularization. So it is separable if only phi theta is separable. By separability, I told you last time also that if you have theta vector, which is you are taking as an L2 norm, it is nothing but theta 1 square plus theta 2 square plus theta 3 square. So if you can represent the individual components of the theta separately and you sum them up, similarly for modulus also, if you are taking an L1 norm, then that is nothing but theta 1 1 plus theta 2 plus theta 3. So if you can do this separation, then it is then this particular L prime k theta is separable, and it's better to use in these type of situations where your regularization theta is separable. So for L2 and L1 norm, mostly it is indeed true that you can separate the components as a summation. So you have this and this, you have this and this, and it doesn't involve multiplication of the cross term. So if you have a hypothetical regularizer which has multiplications of theta 1 and theta 2, in that type of situation it will not work. So it will work mostly for the regularizers where you have separability. So what we are trying to say is, I am just representing the loss function L prime k as beta k, which was the original thing independent of theta. So this will go to 0 also because it's independent of theta. And then what we are saying is this L prime k is nothing but summation of I running from 1 to m delta I theta I. So what is this delta I theta I? I will explain you now. So delta I is nothing but this expression. So if you see, I am writing delta I as nothing but this expression. So what is this expression? This expression is zi minus theta I square plus lambda eta zeta I theta I. So so zi theta I are running from 1 to n. So here you can see what we are doing is we are actually breaking this. We are breaking this expression which is over here into vectors, components of the vector. So this is a complete vector z, and if I want to represent a specific component of this vector, what I will write it as zi. So that means you have z as z1, z2, z3, right? So if I want to represent specific component of this vector z, I will write it as z subscript I. So I am writing this in component wise, like I want to individually check the components of the vector, not the complete vector itself, because this is a complete vector and I want to check for individual components of this vector. So if I want to write in terms of the individual components of this vector, that is nothing but, sorry, not for this one, for this one. This expression is for this one. This expression is basically for this expression. So for this I will be writing for all the individual components. So if I want to write for the individual components of z, it will be zi. If I want to write for the individual component of theta, it will be theta I. And if I want to write individual components of phi theta, it will be phi of theta. If you remember, let us say if it is theta square, then it is theta 1 square plus theta 2 square plus theta 3 square, like that. So it is nothing but I running from 1 to n. N is the number of features, theta I square. So you can write like this, right? So what happens is I am writing for a specific individual component as phi I, the subscript I here. So that's why what we can write it as zik, which is the individual component, theta I is the individual component of theta, lambda times eta, and then xi I theta is this expression. So what I am writing phi theta as summation of xi I theta I. So this is zeta I theta I. So this is actually nothing but theta 1 square plus theta 2 square plus theta 3 square, all that type of stuff. So it is a compact way of representing it. So what I am doing is I am actually now doing component wise minimization, or you can say, we are working on the specific component of the vector theta. So if you do that for all the values, right, from 1 to n, you will get the complete vector, which is theta k plus 1. So we are actually doing individual minimizations of each of these theta i's, and where theta I or zi or xi I are actually the vector, the components of the vector z and theta. So you are actually working on the individual components, and then you sum of these individual components to get to the complete vector theta k. So if you have any questions here, you can ask. So it's a scalar minimization rather than the vector minimization. So let us see a small two examples based on L1 and L2, which will actually clear the doubts that how we are writing these type of summations. So here your L theta is basically a ridge regression loss. So this is basically what? This is a ridge regression loss. So here you can see what is the first step. The first step is to initialize these values to a specific component. So here we have theta 0 as 0 and eta is in between these two steps. So this is the initialization which we have done. The second step is to form the gradient descent equation, and from there you will get zk, and then you can use this zk back into this argument to get to the theta k plus 1 vector. So let us see how we can do it for L2 regularization. And recall that I already told you that proximal gradient descent can work for both L1 and as well as L2. So the same thing can be easily approached through proximal gradient descent also. But you know the answer for this expression also, that is x transpose x plus lambda I, the closed loop answer. So if you evaluate either through that algorithm or through this algorithm, the answer will come out to be the same. But we are trying to tell you that how using proximal gradient descent you can actually get to the local minimum of this loss function. So here you can see the first step is the gradient descent. So you can easily find out the zk for this particular expression. So this is nothing but this one we already know. And then what we are doing now is we are actually writing theta k plus 1, which is a complete vector, which is nothing but it's a summation of I running from 1 to n, which is the vector of size n, because these are the features. So what you are doing is you are actually writing the individual components of this matrix. So zi theta I plus lambda times eta, and then for zeta I is nothing but theta I square. So if you remember, I already told you that if you want to write a specific component of theta L2 norm in case of ridge regression, which is nothing but theta I square. So this is basically the specific component, and your I is running from 1 to n. And whatever answer that you will get for minimization of this particular expression is nothing but the theta k plus 1, the complete vector. So here if you look for the individual component, let us see only single ith component. So if you see a single ith component, it is, and if you take the derivative of that, so if I take only zik minus theta I square plus lambda eta theta I square, so if I take the derivative of this expression with respect to theta I, then what will be the answer? So the answer will be this. So so you are taking the derivative of the loss with respect to theta I. So once you take the derivative of the loss with respect to theta I, you will get this answer. So this is normal, you can do the derivation easily. So it's a derivative with respect to theta I, and from here once you manipulate the values you will get theta I k plus 1. So this is the individual component right now. So for individual component what it is happening is you are actually, whatever result you are getting for zk through this expression, whatever result you are getting, what you are doing, you are actually dividing it by 1 by lambda eta. So what is this doing? This is basically, the individual components of the theta vector, which is theta I, are scaled by 1 by lambda eta times the individual component of the zik, which you obtain through this gradient descent step. So what it means graphically is that if you have taken a gradient descent step zk like this, then in the second step what will happen is this vector will reduce to this vector when you apply the second step of the proximal gradient descent, which is theta k plus 1. So it is basically shrinking this vector zk to theta k plus 1. So if you have gradient descent which is going through this curvature, so let us say you have this contour plots, and what you are doing is you are performing the gradient descent like this to reach to the minimum value. Let us say your maybe your minimum value is somewhere here. So what happens is in this first step you are going through zk, and then when you apply theta k, what will happen? It will shrink its space to this. So it will go back to this point, and now again you will do a gradient descent in this direction, and then what will happen? It will again shrink this back to a smaller size of theta k, and then again you take a gradient descent in this direction. So this way this algorithm will go and find the minimum value, whatever that minimum value is. So in each of these steps, first step it's zk, then this vector will become small and then it will become theta k, and then again you go for another step of zk, then you again project it to theta k, and in this fashion you keep on going and you will hit to the minima. So this is basically the concept of this factor 1 by lambda eta, which you are multiplying with the zeta with the z component of the z vector z, which you are obtaining through this gradient descent. So this is basically for L2 regularization, and if you want to go for L1 regularization, which is our main target, because we started out with the discussion that how to solve for this lasso regression, which has this discontinuity problem. So let us see how we can solve it through proximal gradient descent. So this step is the same step, because this it doesn't involve anything else except these matrices, the design matrices, so and the label y. So we can easily do a gradient descent on this variable zk, which is the dummy variable here, which came through the derivation, as you know. So this step is constant for both. But now in the second step, what happens is you want to find the value of theta k, which is which will be like this, and now we want to find the minima of this particular expression. So what we do is, again we will go for scalar minimization of this expression, because this is the complete vector, and similarly as we had done here in case of L2 regularization, we went for this scalar minimization where we ran this I from 1 to n and we wrote the components of all these vectors. So similarly we will do for L1 regularization, and here you can see we can do it for all the components of the z and thetas, and you can see now individual component of the regularization is represented by theta I. So this is basically the absolute value of a specific component of theta vector, and we are summing it from 1 to n. So this is basically your complete optimization strategy. So now we will again consider one specific ith component of this summation. So if I take a specific component of this, which is nothing but this. So if I try to optimize a specific value of theta I can do it for other thetas also, and then we can concatenate into a single vector which will give you a complete vector theta. So I am currently seeing that what is the state, how this theta I, a specific component of this theta, will change with this zi. So this is the absolute value of theta I. So we will consider two different cases. First case is that when theta I is greater than 0, and in the second case is when theta I is less than 0. So in both the cases we will see how this expression will change. So when your theta I is greater than 0, you know that absolute value of theta I, when you consider the case of theta I greater than 0, you can simply write it as this. And this is also, it's simple, right? And you are trying to find the minimization of these points for this particular thing. So once you do the derivative of this with respect to theta I, you can find out the expression for theta I here. So here you can see theta I is related to zi by this expression. So you can see your theta I is equal to zi minus lambda eta by 2. So this is basically the expression for your theta I when your theta I is greater than 0. So you can see now the constraint is that your theta I has to be greater than 0, then only this is valid. Why this is so? Because you have assumed in the initial stages that your theta I is greater than 0. So if your theta I is greater than 0, then this expression is valid. And if you try to combine these two equations together, then the interpretation of this is basically if your zi is greater than lambda eta by 2, this is basically the interpretation. That is, if your zi is greater than lambda eta by 2, that means if your zi is greater than lambda eta by 2, that is as a result of which what will happen? Theta I will be greater than 0. So if theta is greater than 0, you are comfortable because here also theta is greater than 0. So in that case, your theta I is same. But if your zi is less than lambda eta by 2, then what will happen? In that case, when your zi is less than lambda eta by 2, your theta I will become less than 0. So if your theta I becomes less than 0, it is not in this range. That is where theta I is greater than 0. It's not in that range. So what will happen? It will make it value equal to 0. So the theta I will become equal to 0 here. So if you draw the curve of theta I with zi, what you observe is that with this threshold of lambda eta by 2, which is we are discussing here, this threshold, below this all will be 0. As you can see here, this theta I is 0, and above this you will have the equation of the line, which is zi minus lambda eta by 2. So this is basically the equation of this line. So you can easily verify that this line actually satisfies this equation. So here you can see now two important things. In the case of lasso regression, you are actually selectively passing some of the features, and you are actually rejecting some of the features which are less than lambda eta by 2. So if you recall, in case of lasso, what we were saying is we started out with lasso with the motivation that we wanted to look for features which are really important for our problem, and we do not want to go for the features which are not important for us. So lasso regression is actually helping us in achieving that. As you can see, for this range, your features are all suppressed to 0, whereas in this case, your features are passed. They are passed, and here it is all zeros. So they are all zeros. So you are selectively passing some of the features, and you are selectively and you are rejecting other features because this is 0 here. So now we have considered theta I greater than 0. So if theta I is less than 0, in this situation also we have to work because we have modulus function, right? So in modulus we have to go for both the cases when you have plus theta and when you have minus theta. So when your theta is less than 0, if you do the derivation yourself, I'm not going into the details of it, it's very easy. Just follow the steps, you will get to the answer. So once you do it, what you will get is this expression. So here in this expression, what it says is that theta I is related to zi by lambda eta by 2. So you are adding something to this zi. And the second constraint is that your theta I has to be less than 0. So now the other interpretation of this is that if your zi is less than minus lambda eta by 2, in this situation what happens is your theta I will be less than 0 and it is satisfying this constraint, so your theta I is okay. So you will get this answer. But if your zi is greater than minus lambda eta by 2, in that case what will happen is theta I will become 0, because at that time your theta I will become positive and we do not want it to be positive, it has to be less than 0. That's why it will be 0 here. So if you plot this equation, if you plot this condition, what you will get is this expression. So for theta I greater than minus lambda eta by 2, your answers are 0, and for less than that you will have this line. So here you can see again these features are all reduced to 0 and these features are all actually passed and they are having the importance. So as you know that theta, the modulus theta is a combination of less than and greater than 0. This is the less than 0 condition and this is the greater than 0 condition. So we have to actually join these two conditions to work for the modulus function. So these are the two separate conditions which we have discussed. So now we will join them together. The two curves will be joined and you can see once you do that you will get this answer. So this is the case when you have theta greater than 0 and this is the case when you have theta less than 0. So if you want to write this equation for this particular curve, it can be represented like this compactly. So in a mathematical way it can be represented like this. So this means if your features are actually lying in between these two ranges, then all that features will be bring down to 0. You can see theta is our features, right? The model of the parameters. So you know if the model of the parameters are brought down to 0, then you have these features multiplied with this model of the parameters. So if this is 0, then this will automatically become 0, right? So the contribution is getting 0 here for the specific features, and here you are passing the model parameters with no problem. So the corresponding xi's which are multiplied with this theta i's will be the features which we are looking for. So these features will be passed, these features will be not passed. So this is also called as soft thresholding, because you are doing a thresholding. A thresholding operation means below it is 0, above it is passed. So it is called as soft thresholding because this is a softer version of the thresholding. The hard threshold is like this. So if you threshold like this, then this one is called as hard threshold. Hard threshold, because you are not allowing anything below above this. So it is actually making either 1 or 0, but this is a softer version of it. So that's why it is called as soft threshold. And this type of thing is hard threshold. So any questions here related to what I have explained? Am I connected or I have lost the signal? Are you able to hear my voice?
Yes.
Okay.
Yes.
Okay, so if it is clear to you, then we will move forward and see what exactly is happening actually when you do a L1 regularization onto the contour plots. If you remember, for L2 I have shown you the contour plots which looks like this. So we will do that same thing for L1 regularization and see how we will go to the minimum value by passing through these gradient plots. So let us see that here. So in case of L1 regularization, if you do this, so here you have the contour plot. So here you have this contour plots, and you want to go to the value which is a minimum, or you can say some optimal value. This is just a diagram to show you. So this is basically what it is trying to show you is the steps that you are requiring to go down the hill. So this step is the gradient descent step, which is involving the parameter zk. If you remember the first one, this is the first step of doing a gradient descent, and this is basically zk. So here you can see we have this zk here. So zk is basically the first value that you get through this step, and now you can see that we have these two thresholding values also given. This is lambda eta by 2, and here also we have lambda eta by 2. This lambda eta by 2 is basically coming from this particular thing. So what you see now is that this vector actually has a value greater than lambda eta by 2, because this is the lambda eta by 2, right, for theta 2. For theta 2, if you so when you have this z vector, the corresponding components of this z vector will have values. This value is greater than this, and this value is also greater than this. So if this component is also having a value greater than this, and this component is also having a value greater than this, what will happen is it will shrink it down to the value less than to lie within this range. So what happens is it will subtract this value to this side. So basically both the values here and here will be brought down, and they will be subtracted with this lambda eta by 2 and this lambda eta by 2. Why it is subtracted? Because you can see here, this is the subtraction which is going on in these situations. So if it is greater than this lambda eta by 2, the components of the vector z, if it is the components of the vector z are zi, so if they are greater than lambda eta by 2, you will subtract the values. So here you can see the components of this z vector is this, another one is this. So they both are greater than lambda eta by 2, you subtract the value, and so now the new z will, now the new one will be this. So this is basically your initial theta 0, and now once you are at this point, this is again becoming your new next theta 1. Now again you will do a gradient descent. Once you again do a gradient descent, what will happen? You will go to this point. So this is actually z2 now. This is z1, this is z2. And here you see in this particular z2, the component of this z2 is less than lambda eta by 2, so you will not touch it. Oh sorry, you will actually make it 0. Because you can see here, if you are less than lambda eta by 2, you will make that value 0. So this component of z vector is less than lambda eta by 2, so you will make the y component of this vector 0. So if you make the y component of this vector 0, it will immediately come at this point, whereas the second component is already greater than lambda eta by 2. So what happens is you are subtracting that value by lambda eta by 2. So that's why you will go back. You will not go like this or this, you will go back, because at this point the component is greater than lambda eta by 2, and it will be subtracted from that, so it will go back and it will lie on this axis theta 1. So now here you have the new theta, which is theta 2, let us say. Now you again do a same thing, and here you have z3, and again same situation happens, that the component of this z is less than lambda eta by 2, so it will again make it 0. So you can see now it will start oscillating here, and you will hit the minima. And the problem is, and the important thing is that at this point where it reaches, you can see theta 2 is 0 here, and theta 1 is having some value, so it is giving you a sparse solution here, because here you have one of the components theta 2 as 0 and theta 1 is having some value. So this you can see how sparsity or how sparse solution you are obtaining here when you force the solutions to when you do these type of thresholding operations which are done over here. So I hope you can understand that how this contour plots are moving as far as the L1 regularization is concerned. If you have any questions here related to this, you can ask, else I will move forward otherwise. Okay, so now just two applications to show that this thing is really helpful for us. The first application is that most of the images that you have in real life, they are sparse actually. So how we can show that? If you take this image, let us say, or you can take any of the images whatever you wish. If you plot the histogram of this image, then this histogram will look like this. So it's a histogram of this image. So if you do not know histogram, you can better look onto the image processing books. I will not go into the details of it. So if you do not know that, and if you know, it's good. So just try to see, in case if you do not know, just see what this histogram is. So it's basically, once you plot the histogram, you will observe that this histogram is very dense, and you can see you will have all the values in this histogram. Whereas if you convert this image by using there is one transform which we are calling as discrete cosine transform. So this is discrete cosine transform. So if you apply a discrete cosine transform on this, then what you get is, you get this curve. So from this curve and from this curve, what you observe is that only few components are 1, except all of them are 0 in case once you take discrete cosine transform. So that is what excites the most of the companies, that you can actually convert this image into discrete cosine transform, and where the components will be, very few of them will be 1 and rest of them will be all 0. So this is basically sparse components. And what happens is, we can use these components to transmit our images. So here you can see I have given you a screenshot of the WhatsApp thing. So once you forward your images on WhatsApp, what it does is, it will be in 2 stages. It will be in preparing stage, and then it will be in sending stage. So in preparing stage, what it is doing is, it is actually converting this image into this vector. So once it is converted into this vector, you can see the amount of space that is required to store this image. Earlier you had to store these amount of values, but now in order to store this big image, you only need few coefficients, and rest of them are all 0. So you can use this particular expression to send to the other side, and when your friend or any of your relatives will be seeing your images, what will happen is, it will actually the software will actually convert this particular thing back into the image. So you can see now that while transmitting, you are transmitting very less number of coefficients. Otherwise, if you are transmitting these coefficients, then you can see how much amount of bandwidth is required to transmit these amount of pixels. Whereas now you are only transmitting very few pixels. So these pixels, when you transmit onto the medium, on the other end, when you will receive it, it converts these coefficients back into the image, and you can see your image. Okay, so this is basically the advantage of sparsity. That is, your vectors are sparse in some domain, which we are calling as discrete cosine domain. So in this domain, it is sparse, which people have seen it. So they make use of this sparsity to get to the transmission. So it makes the transmission easy. So this is first application. The second application is this is again showing you that same thing. So this is the original image, and if you take only few coefficients. So here let us say we have this coefficients like this. So they are not exactly 0. Some of them will be having some value. So what we do is, we apply thresholding operations. So what we say is, let us keep only these coefficients, and let us make all of them 0. So if you do that, you will get this image. And if you take only one pixel and make all of them 0, then you will get this image. And if you make these amount of pixels as 1 and rest of them are all 0, then you will get somewhere in between. So this is showing you the quality of the images when you retain some when you retain 10 coefficients, when you retain 5 coefficients, when you retain 2 coefficients. So this shows you how the quality is also reducing when you retain the how many coefficients you are retaining. But you can see that on retaining only 5 coefficients also you are getting the good image back as compared to the original image. So same quality is still there, it is not reduced. But but if you keep only 2 coefficients, then you can see that the quality is reduced. So the companies, software companies, actually try to find the sweet spot where they can retain the quality also as good as can, and the coefficients also they can keep them small. So that is the research actually, that most of the companies are using that that optimal figure where the coefficients are also less as well as the quality is also good. So they try to do that. So this is also showing you that same thing, that is, if you retain very less amount of coefficients, your quality of the image will be drastically reduced. But if you keep reasonable amount of coefficients, you will get the same image as back as the original image. This is another example which shows you why lasso regression is helpful. So here you can see we have crime rate in the city. So what we are trying to do is we are trying to predict the crime rate here. We are trying to predict the crime rate here. This is y, and this is all features. So we have x1 feature, this is x2, this is x3, this is x4, this is x5. So these are all features. Okay, so what we are trying to do is we are trying to find out which of these features are actually helpful in determining the crime rate. Right now you have 4 features, but we do not know which one are actually helpful, or you can say which of them are not really that helpful. So we want to find out the features which are actually helpful in contributing to understand crime rate depends upon which one the most. So if you recall, this was the motivation from which we started out for lasso regression. So here you can see these are the 2 optimization strategies which I think you must be knowing now. So this is the L1 one, and this is the L2 strategy that we are using for getting the optimized values of theta. So if you do it through lasso regression, you will get theta 1 hat. If you do it through L2 regression, which is if you do it for L2, you will get theta 2 hat. So these 2 are the optimal parameters that you will get for lasso, and this is for ridge. So what we are observing here is we are trying to plot these values. So this is the theta 2 parameter. So here you can see all these curves which are shown with different color are basically the features. These are the features here: x1, x2, x3, x4, x5. You can see here funding, HS, not HS, college 4. So these are the feature contributions, the curve which is shown over here are the feature contributions. Similarly, on the right side also, it's a feature contribution coming from lasso. This is the feature contributions which are coming from ridge. So now what we observe is that if you reduce the value of lambda, so right now lambda is, let us say, 10 to the power 8. So if you reduce the value of lambda, so for any value of lambda, if you see the region, for any value of lambda, in case of ridge regression, you will see that all these parameters or all these features have some contribution for that specific value of lambda. So let us say if I take this lambda, and if you plot the line here, you can see all of them will have some value. All the features will have some value. If you go here, then also, except this green one, all of them are having some values. So that shows that your ridge regression is actually giving weightage to all these features in some amount, and it is trying to address all of them at the same point. And so you cannot judge that which of the features are really important to decide the crime rate in the city. Whereas in case of lasso regression, if you observe that if you select the lambda here at this point, then you can see only green feature is important. You can see only green feature is important, which is basically nothing but this high feature, and rest of the other features are all 0 at this location. So you can observe now that at this location only this feature is important, rest of them are all 0. This means this is the one which is actually acting as an important feature to detect the crime rate in the city. And if you further reduce the value of lambda, then at this point you can see, if you go here, you will see the blue feature is important and contribution of green feature is important, and rest of them are all 0. So this means whatever value that you are getting are sparse vectors, because out of 4 vectors, these 2 are there and the rest of them are all 0. Similarly, if you keep on reducing the values of lambda, you can see that the contributions of one dominant feature is there, whereas the rest of them are all zeros. So you have to be in the region where this situation happens, and that can be done through lambda, which is the regularization parameter, which helps you in doing that. So this is basically showing you a contrastive study where lasso is actually helping you to selectively make one of the feature dominant, whereas the other features are not made dominant. Whereas in case of ridge regression, all the features are equally made important, and it gives importance to all the features in the same way, whereas in this case it's not like that. So this actually finishes off with your linear regression.